Hello again and welcome back to our course on Excel 2019 Advanced. So far in these sections on statistical functions, we've looked at descriptive statistics where we summarize statistical data, and we've also looked at prediction or forecasting. In this section, we're going to look at statistical functions for inference, and typically when we're looking at inferential statistics, we mean that we take a sample of some sort, and on the basis of that sample, we make statements about the population from which that sample has been taken. Now, I'm going to base this section on a very straightforward example, and in this example, a doctor's surgery have taken the heights of a number of female patients. The heights are shown in inches in column B. And what we're going to do is use that sample to infer some properties of that population from which the sample was taken, and also to infer the likelihood of women having particular heights within the population. Now, in doing this, I'll be making quite a lot of assumptions, and if you have a reasonable knowledge of statistics, you may be familiar with some of those assumptions and some of the issues that arise. But one of the main assumptions I am making is that given a particular doctor's practice and the area that it covers, that sample is big enough to represent the population of all female patients. And the second major assumption I'm making is that within the population as a whole, the heights of females are normally distributed. So that's the familiar bell-shaped curve for distribution of heights. Now, if you don't have a solid background in statistics, you may listen to both of those assumptions and say, how can you be certain that those two things are true? Well, there's very rarely certainty when you're dealing with statistics, but there are tools and techniques that we can apply in a situation like this one to establish with sufficiently high level of certainty that both of those assumptions are true. And although I'm not going to go into those now, we are going to proceed on the basis that both of those assumptions are reasonable. So that's a big enough sample to represent the population and the population from which these heights have come from. Now, the sort of question I'm going to ask is this: what proportion of females within the range of this doctor's practice would be less than 5 feet tall on the basis of this sample data? Now, we're going to use one of the other statistical functions to do this, and in order to apply the statistical function, we need the mean and the standard deviation of this sample. So you know how to calculate those, but I'm just going to do those again. So there's the mean. And for the standard deviation, we're dealing with a situation where we're going to use a sample to estimate the standard deviation of the population from which the sample was taken. So we're going to use the stdev.s function, as I explained earlier on. So there we are. That's our mean and standard deviation. We're now going to calculate the probability that a woman chosen at random from this population will be less than 5 feet tall. Now, the function we're going to use to calculate this is one of the normal functions. And if you look at the list of normal functions, there are 8 of them. And the first 4 are the ones that we normally use, whereas the old 4 are the ones with the yellow triangles. These are the ones that the new 4 have replaced. Now, the function we need is the very first one, and we specify first of all the value of x, the value that we want to find the probability that a member of the population chosen at random will be less than. And that will be 5 feet, which is 60 inches. The mean height is in E2. The standard deviation is in E3, and that just leaves us with 2 functions, true or false. True uses the cumulative distribution function, and false uses the probability mass function. Now, there's a very important distinction between these two, and the true cumulative distribution function is the one that we use for continuous variables like height. If we were dealing with a discrete variable where you could have exact values, so these are things that are accounted rather than measured, we would specify false here. So in our case, this is a continuous variable, so we would need the cumulative distribution function. So the value we need here is true. And we find that on the basis of our sample, the probability that a woman is less than 5 feet tall is 0.2, which is 2%. Just as an item of technical information, with a continuous variable like height, as far as statistics is concerned, the probability of being exactly 5 feet tall is 0. So if you said, what's the probability that a woman is less than or equal to 5 feet, the answer will be the same figure. So what about the probability that a woman is more than 5 feet tall? Well, given that all women will either be less than or more than, and I ignore the equal to for reasons that I just said, then if 2% of women are less than 5 feet tall, 98% must be more than 5 feet tall. So expressing this as a probability, a number between 0 and 1, the probability that a woman is more than 5 feet tall is actually 1 minus E5. And the answer is 0.98, as you would expect. So on the basis of one probability, less than, we can work out the probability of greater than. What about the probability that a woman is less than 6 feet tall? So we're going to use the same function again. This time the x value is 6 feet, and that is 72 inches. And we find that 95% of women are less than 6 feet tall. And of course, you know now how to work out the probability that a woman is more than 6 feet tall. Now, what about the probability that a woman is between 5 and 6 feet tall? Well, the way that we work out probabilities between two values is by subtracting one from another. If we know that 95% of women are less than 6 feet tall and 2% are less than 5 feet tall, then the number between those two will be the 95% figure minus the 2% figure. So the probability that a woman is between 5 feet and 6 feet tall is going to be equal to E8 minus E5. That gives us a figure of 0.93 or 93%. Now there is a different sort of question that we can answer using these functions, and the question I'm going to ask this time is, what is the height that 25% of women are less than? In other words, what is the woman's height lower quartile? Now, when I chose the norm.dist function just now, you might have thought to yourself, well, why did you choose that one and not one of the others? Well, we're now going to choose one of the others because the norm.dist function finds a probability when we know, in this case, a height. The norm.im function is the one that gives us the height when we know the probability, so essentially the inverse. So we want equals norm.inv. Now the probability we want is 0.25. The mean is E2. And the standard deviation is E3. So the lower quartile height is 64.4 inches. Now let me do the same thing for median and upper quartile. And there we are. Lower quartile is just under 64.5 inches. The median is just over 5 feet 6.5, and the upper quartile is just under 5 feet 9. So the dist function gives us the probability from, in this case, the height. Inv gives us the height from the probability. There were two other functions, norm.s.dist and norm.s.inv. These basically do the same job, but for what's called a standardized normal distribution. which is a special case of the normal distribution in which the values are scaled down to be in the range 0 to 1, but we certainly don't need to use that here. If you're going to look further into statistical inference, it's very likely that you will come across that special case. In the meantime, norm.dist and norm.inv are going to do the job for you. Now, if statistical inference is new to you, then you will probably be mainly dealing with normal distribution cases, but in fact, Excel 2019 now can deal with a number of different types of distribution, and there are dist and im functions for a number of different distributions. For example, you can see here binom.dist and binom.im for binomial distributions, and there are various other distributions that you might want to look into. But for now, that's it on statistical inference and statistical functions in general, so I will see you in the next section.